Hey folks, welcome back. We are continuing on with particle motion here. So if you haven't watched the video where we go through all of these topics, you're definitely going to want to watch that first, okay? Some of the stuff I added after, you won't need that. That's just for me going forward. All right, here we go. Our first particle motion problem. A particle moves along a horizontal line so that its position at any time t is greater than 0 is given by the function x of t equals t squared minus 4t plus 3, where x is measured in feet and t is measured in seconds. All right, so the first thing you always want to do is read for information. You want to annotate if you see something that jumps out to you. So the first thing I noticed as I was reading through this is that x is measured in feet. These are units. And time t is measured in seconds. These are units. So that means every one of our answers, when we talk about our rates of change and when we talk about when this is occurring, we always have to include some units. Something else that I'm looking at as I'm going through, a particle moves along a horizontal line. Okay, so that means if I'm moving horizontally, I'm either going left or right. Now, if I had a vertical line, my particle maybe is moving up or down. So that its position at any time t is greater than 0. All right, here's another thing I want to annotate. When we're talking about time t is greater than or equal to 0, the way we're going to write this up is that t is an element of, I'm going to actually write this up as time t is an element of, we're going from 0 and on. So we're going to write that as 0 inclusive until infinity not included. So you can write it up using, this is called set notation. I am going to write all of my stuff using interval notation. So we know that our particle is moving left and right. Its position is based on time from 0 and on, and it's given by the function x of t equals. Okay, now I probably shouldn't do it at this point because I don't know for sure. But what I like to do is I know I'm probably going to be doing velocity here, and I'm going to be doing acceleration. So what I usually do is I go ahead and I derive these right off the bat. So let's do a quick review up at the top here. We have, yeah, I can probably, we have position, x of t. Then we have this thing called velocity, which is v of t. Now, position, sometimes they'll use s, sometimes they'll use p, sometimes they'll use x, sometimes they'll use y, because in this case, x makes a lot of sense because we're moving horizontally. If this was a vertical line, we would probably use y of t. But those are the position equation changes its letter all the time, and I'm not sure why. The other two don't. It's always v and it's always a for velocity and acceleration. All right, so what's velocity? Well, velocity is the derivative of position. And then we have this thing called acceleration. And what do we know about acceleration? It's the derivative of velocity, which means then it must be the second derivative of position. So writing those relationships out and memorizing them, then writing them out, I have found to be pretty helpful as I go through this. So what I want to do now is I want to add those, I'm going to add those functions for acceleration and velocity down here. So let's do velocity next. V of t, which we know is the derivative of position. So the derivative of position would be 2t subtract 4. And then we would have acceleration. Acceleration is the second derivative of position. So if you want to derive it, or you could just take the derivative of velocity, which is a lot easier. So that's just a constant of 2. So our particle is constantly accelerating 2, and then we'll talk about units when we get there. All right, let's get after it. Find the displacement of the particle during the first 3 seconds. All right, displacement. What does this mean? What is displacement? Displacement is how far, this is distance. This is distance with direction. So what that means is how far did you travel and which way did you travel? That matters. That's different than just distance. If I walk 3 steps forward or if I walk 3 steps backwards, I've walked a distance of 3. But when it comes to displacement, if I walk 3 units backwards, I've been displaced -3 steps or however my distance is. And we find displacement by taking the final, subtract the beginning. I don't know why I put parentheses around that, but I did again. It's the final, subtract the beginning. So let's figure this out. When is our... So we're talking about for the first 3 seconds. So what's our final time? Our final time would be 3 seconds. So it's how far did we move in 3 seconds? So I would say x of 3. That would tell me where I am after 3 seconds. That would tell me my position after 3 seconds. And then I want to subtract my position at 0 seconds. And how would we find these? We'd just plug and chug. X of 3, so I would plug 3 in. That's 9. Take away 12. 9 take away 12 is -3 plus 3. Oh, is 0. Subtract x of 0. That'd be 0. That'd be 0. That'd be 3. So we get -3. Okay, now as our write-up. Explain its meaning. That just means do a write-up at the end. So now our write-up is going to be the particle was displaced -3 feet. Notice I put my units on there. During the first 3 seconds. If it said find the distance, actually we're going to do that later on down at the bottom. Find the total distance during the first 3 seconds. That's going to be a little bit more complicated. All right, find the average velocity. Let's annotate again. I want to leave myself a little note here. Average velocity. So as soon as I see that word average, most of the time that's an AROC. That means I need 2 points. That's an average rate of change between 2 points. So during the first 3 seconds, so our 2 points are going to be 0 seconds and 3 seconds, first 3 seconds. Now, average velocity, this is the average rate of change of velocity that we're going to, so we're going to use how much, how do I want to write this up? Velocity average is going to be equal to the change in, so if I want to figure out velocity, it's not the change in velocity, which is very interesting to me. I struggle with this. Average velocity to me kind of feels like I should figure out the velocity and then the other velocity and then divide by 2. No, that's not what we're trying to do here. We're trying to figure out the slope to find my average velocity. So that means I'm not going to take the change in velocity. To find velocity, I'm going to take the change in position over the change in time. I want to see how far I changed in position divided by how much time transpired. So for us, it would be, remember, we're doing the first 3 seconds again. So I'm going to figure out my velocity average would equal x of 3 subtract x of 0 over 3 subtract 0. See, what I'm doing is I'm finding the slope of position. I'm finding the change in position over time, and that's going to give me my average velocity. So x, we already calculated this to be negative 3. 3 minus 0 is 3, and we get negative 1. This says explain the meaning, so that means we need to do a little write-up. And by the way, you always need to do a write-up, so just get in the habit of doing a write-up every single time. Even if it doesn't say it, you usually want to write it up. So let's see. I think there's 2 ways that I can write this up. I'm going to try to write them up both ways. On average, I wish I would have just done AVG, but I didn't. On average, the particles velocity is, and here again, you can just write changing. I don't like to write changing. I like to say what it's doing, is decreasing by 1. Okay, units. 1, so delta x over delta t. So change in position is going to be feet. Change in time is going to be seconds. So there's my units. By 1 foot per second during the first 3 seconds. I always get stuck here. I always got to think about this. On average, the particles see, no, that's not right. That's not right. It shouldn't say velocity here. It should say position. The particle's position is decreasing by 1 foot per second. If the velocity was decreasing, it'd be decreasing by 1 foot per second per second. That's the change in velocity. So on average, sorry about that, the particle's position is decreasing. What would I say? Oh, okay. The other way I could say this, the other way that I got it. Okay. The other way that you could say this stuff's tough, guys. So if you're struggling with it, I get it. So as you can tell, so do I. This stuff's not easy. Okay, so the other way I could say this is the particle's velocity is negative 1 feet per second. I always have to write that on average. On average, during the first 3 seconds. So you see how the 2 different ways I'm talking about it? I like that I caught this eventually. On average, the particle's position decreases by a foot per second during the first 3 seconds. Or you could say on average, the particle's velocity was negative 1 foot per second. Those are saying the same thing. How my position changes is the velocity. Change in position is velocity. Change in position over time, I should say. Change in position over time is the velocity. All right. Find the particle's initial velocity. So this is a little bit, I don't know if you guys have done this in physics. This is where I learned phrases like initial back in physics. Initial velocity. This is the velocity at 0. This is when time equals 0. That word initial means time equals 0. So position velocity at 0 would be the derivative of position at 0, okay? And then we're also going to figure out the velocity at 3 seconds. You know what? I'll do the work here and then do the write-up because it looks like I have to explain the meaning of each of them. Okay, so initial velocity is when time equals 0, and then later on here I have, what would be a good color? At time equals 3 seconds. So now this is the velocity at 3 seconds, which is the derivative of position at 3 seconds. So these are both, by the way, IROCs. I guess I could write that in there too. These are both IROCs. There's instantaneous rates of change. All right, so we've got a formula for velocity. We already wrote that up above. We've got some values that we can plug in. So let's just go ahead and plug in 0 into this. So V of 0. If I plug 0 into this thing, I'm not going to show my work. 2 times 0 minus 4 is -4. Now I'm going to go ahead and do this one at the same time. Plug in 3. 2 times 3 is 6. Take away 4 is 2. Now, if you want to write units here, you can. I always just write my units at the end. That's probably a bad habit. That's probably a bad habit, isn't it? Maybe I should go back. I'm going to go back and actually add units to everything that we've done, even here, because I don't think you have to write up units at that point, because, I mean, that's not your write-up. That's just showing your calculation, but let's just be safe. So what's velocity measured in? We figured out velocities calculated by feet per second. It's probably a good habit anyway. What, it'd take us 2 seconds to write them out. Okay, so now let's do our write-up over here. So this says, explain the meaning of each in terms of the particle's movement. Interesting. It wants us to talk about the particle's movement. So what happens, this is where we go back to this side. What's happening to our particle if our velocity is, our first velocity was -4? So what does that mean at time 0 that our particle is, velocity was negative? That means that our position is decreasing, which means it's moving left or down. So for us, since we're in a particle is moving horizontally, our particle is moving left. When the velocity is positive, position is increasing, which means it's either going right or up. So we would do a little write-up over here. The particle is moving left at a... Now here you can write a couple different things. You can write the word speed if you want to, but if you're going to write the word speed, you can't have the negative in there. Remember, speed is the absolute value of velocity. So speed is just a number. It's never negative. Direction doesn't matter. I'm going to actually just write speed. The particle is, you could also just write velocity of -4 too. But if you're going to write velocity, you should probably write no. Let's just write speed. Let's just do this one way. The particle is moving left at a speed of 4 feet per second at time t equals 0. Why did I lose a point? I lost a point in this example. I know it's annoying because I didn't write 0 seconds. It seems like such a little thing. But the College Board is picky about it, so I'm going to be picky about it. Because the velocity was negative, our particle is moving left at a speed of 4 feet per second at time t equals 0. So at that one moment in time, actually, I'm going to put that in here. This is my moment. Let's go back up here. This is my moment in time. No, never mind. No, I'm not. That's my moment in time. I don't want to have to keep writing it. I thought I had more room at the top, but anyway, okay. Let's have you pause here and try to do the write-up for this one. Pause it. I've been doing a lot of the work. Let's have you pause it and try to write it up on your own. All right, let's see how you did. So it's pretty straightforward. The particle is moving. Now, because my velocity is positive, that means I'm moving to the right, is moving to the right at a speed of 2 feet per second. And I can't just stop here because when is it moving at a speed of 2 feet per second? Because if you looked at over here, right, it was moving at a speed of 4 feet per second. That's why we have to also have the quantifier, I think, of what time this is occurring. At a speed of 2 feet per second, and sometimes you could say at, or you could say when time t equals 3 seconds. I think you can use just S for seconds, but I really don't recommend it. I would at least do S with the E and the C afterward. Okay, find the acceleration. All right, so here's our first, we're talking about acceleration. So our first acceleration problem. Remember, acceleration, A of t, is equal to the derivative of velocity, which is the second derivative then of position. Find the acceleration when t equals 3 seconds. Here's my time. Explain its meaning in terms of the particle's velocity. So that's going to be interesting. Make sure we go back and reread our write-up. Sorry, our write-up should be written in terms of its velocity. Okay, so let's figure out what's A of t. So we're going to do A of our time is 3 seconds. A of 3 equals, and if you remember, the acceleration function was very boring. It was always 2. So our particle is always accelerating at a rate of 2. So 2. Now, like I said, I'm going to start to put units on these. So let's go over here and talk about acceleration. Acceleration is equal to, I should have done this in a different color. Acceleration is equal to the change in who? So who's one level below acceleration? Velocity over the change in time. So the change in velocity, well, now we got to go back and think about what's velocity. Velocity is the change in position over time. So this is feet per second over change in time is another second. So what happens is this gets flipped and multiplied. Over 1, and then it becomes 1 over seconds. I was going to say secant. So that means that our acceleration is measured in feet on top, and seconds times seconds would become seconds squared. So acceleration is measured in feet per second squared. So that's feet per second per second. Let's do a little write-up now. Now remember, we're talking about the particle's velocity here. So the particle's velocity is, so the acceleration is the change in velocity. So it's how the velocity is changing. The particle's velocity is, since it's a positive 2, I can say increasing by 2, and put your units in there, 2 feet per second squared. And then you always have to say when, because if you look at 1 second or 2 seconds or 0 seconds, this is going to be a little bit different. Well, actually, it won't, will it? But anyway, that's just kind of when, because acceleration is always 2. That's why I said it wouldn't. When time t equals 3 seconds. Now, if it just said explain, you could have said the particle's acceleration is 2 feet per second squared when time t equals 3. You don't have to talk about the changing, increasing, or decreasing, but it wanted to talk about velocity. Now, it would be really weird if it wanted to talk about position here, because you'd have to say then the particle's position, the change in the particle's position is changing by, because it's the second derivative. Anyway, okay. At time t equals 3 seconds, is the speed of the particle increasing or decreasing? All right, so this is a big one. This is where we want to leave ourselves a little note here, a reminder. Increasing speed versus decreasing speed. Now, this is our first example of this, so I understand if you don't have it memorized yet. This comes from this side, though. So I want to talk about when is speed increasing and when is speed decreasing. Speed is increasing if the velocity is positive and the acceleration is positive, or the velocity is negative and the acceleration is negative. So we say velocity and acceleration have the same signs. If you're moving to the right and you're getting pulled to the right, you're going faster. If you're moving to the left and you're getting pulled to the left, you're going to be going faster. And then if your velocity and acceleration have different signs, then your speed is increasing. If I'm running forward, but you've got a rope tied around me and you're pulling me back, I'm going to be slowing down. And then left and then pulled right. So let's go back and leave ourselves a little note here. Annotate this. Even if you haven't memorized, guys, I've been teaching this class for, 3 or 4 years now, and I still write this out as a reminder. Increasing, that means V of t and A of t, same sign. I'm decreasing if V of t and A of t have the same sign. All right, so let's figure this out. What's happening at t equals 3? So let's find my velocity at 3. Well, I think we already did this, didn't we? Yeah, right here. Velocity at 3 was 2. I like units. I like turtles. My acceleration at 3, we just did that in the example up above, is 2. I like units. Now, they don't have to be the same. And if I was talking to Corpy, I'd say, hey, Corpy, let's change this problem so that they're not the exact same number. What matters here is that they have the same sign. And so this is positive, and this is positive. Okay, now since they're both positive, then we can say that our particle, let me try again. Because they have the same sign, we can say our particle is speeding up. So the particle is speeding up. Or I could say the particle's speed is increasing. Maybe that's better. The particle's speed, is increasing at time t equals 3 seconds. Notice I said when. Now that's not enough because it said justify. That's just saying what's happening. The particle's speed is increasing at time equals 3 seconds because acceleration and velocity have same sign. If one was positive and one was negative, then we would say the particle speed is decreasing. All right. During what times is the particle moving to the right, to the left, and at what values of t does the particle change direction? Justify. So we got a lot going on here in that little space. So let's start off with our annotating as always. At what time is the particle moving to the right? Stop there. What does it mean to be moving to the right? How do you know when a particle is moving to the right? It's when velocity is positive. It's not my position is positive or negative. It's because I could have a negative position but still be moving to the right. If I go left, 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 and I stop and start coming right, I would still be negative position, but I would have a positive um, velocity, which would pull me to the right. When would I be moving to the left then? Well, I would be moving to the left when velocity is negative. At what values of t does the particle change direction? So that's going to be those moments when you switch from being positive to negative. So this is the first time we're going to bring out our good friend, the sign chart, from way back the very beginning of the year. This is one of those tough ideas really early on. So I'm going to make a sign chart here. And I'm going to see, okay, when does my particle stop? When does velocity equal 0? That's what I want to figure out first. So I don't know. I want to figure out if I can let me try again. If I can figure out when the velocity is 0, then I can just check on either side of that 0 to see if those values are positive or negative. So I would take my velocity equation, I would set it equal to 0, and I would solve it. Therefore, 2t, let me try again, v of t equals 2t minus 4 equals 0, which implies t equals, bump over the 4 divided by 2 times t equals 2. So at time t equals 2, my velocity is 0. Now I also want to put this at the end here. I want to put an end point here because this function doesn't just go on and on forever, right? We said at the they said at the very beginning that all our times occur for times that are greater than or equal to 0. Okay, so now from here, I now need to. This on the web. Oh my gosh, Siri. Okay, now from here, I need to figure out where is the velocity positive and where is the velocity negative. So what I'm going to do is I'm going to take my velocity equation and I'm going to plug in some value in these intervals because here I know that my velocity is 0 because I solved my velocity equation set equal to 0. If I take 2 and I plug it into this, I get 2 times 2 is 4 minus 4 is 0. So at this moment, my velocity is 0, which means my particle is moving neither left nor right. But what's happening right before that? What's happening right after that? And I want to figure that out. And I just pick something in here and I plug it into velocity. Let's take 1, 2 times 1, 2 minus 4, negative 2. So this section, what's interesting about this, if you can just find one, they all will follow the same because there aren't any more zeros in here. So by the intermediate value theorem, since there aren't any values of 0, then there's no way that these values could change from positive to negative. Okay, over here, I'm going to pick something like 3. 3, 6, take away 4 is 2, so this section is positive. So now what I can do is I can use this sign chart to figure out the answer to these two questions. The particle is moving left. Now, this is the first time that we got to talk about more than one time because it's all these times between 0 and 1. So the way we say this, the particle is moving left for all, remember this from earlier on in the year, for all time t. That's an element of 0 included until 2 not included seconds. I'm going to just keep going here, and I'll explain in a minute. Because, all right, actually, I'll stop and explain. The particle is moving left for all times t between 0 included and not included 2. Notice I put the word time in front of t. I put the units after this. Now, why did we include 0? Because at time 0, what is our velocity? At time 0, our velocity, put in 0, you'll get negative. That velocity is negative. That's good. That means it's moving left at time 0. Why didn't we include 2? Because when you plug in 2, you get a velocity that's 0. That's not negative because v of t is less than 0. The particle is moving left for all times t is in 0 to 2 because the velocity is negative in there. You can't say that at 2. That's why we don't include 2, because at 2, it's not less than 0. It's equal to 0. I'm going to encourage you to pause here and try to write up the next one. When is the particle... Dang nabbit. Why did I do it? My colors are all mixed up. Dang it. This should have been in purple. Stucky. You guys go ahead. Pause it and see how you do here. Okay, let's see how you did. The particle is moving right for all time t is an element of 2, not included, until infinity, not included, seconds, because why? Velocity is greater than 0. My velocity is positive, I'm moving to the right. Okay, now notice we're not done. This was 3 questions. At what values of t does the particle change direction? So when you're going to change direction? That's when you're going to switch from having a negative velocity to a positive velocity, or vice versa. So my write-up would be the particle, I'm going to try to squeeze it in over here. The particle changes direction at time t equals 2 because, how come I just lost a point? Because I didn't put 2 seconds. Annoying, I know, but that's the game. The particle changes direction at time equals 2 seconds because, now why? Why? A lot of kids in the past get this wrong because they say because velocity is 0. No, that doesn't mean you change direction. I can be moving to the right, get to a 0, and then after that, it'd still be positive. So my velocity could be positive and positive before and after the 0. This is an example of a mult2, right? Back in our, if I had a function that had a mult2, if its velocity function had a mult2, before and after the 0, the low point of this parabola I'm pretending to draw, would both be positive. So our particle would be moving to the right. It'd stop because its velocity is 0. That's true, but then it would continue moving to the right. The particle changes direction at time equals 2. It's not because at 2, the velocity is 0. It's because the velocity switches sign at time t equals 2 seconds. So notice, it's not because velocity was 0. It was because velocity switched signs at that value. All right, last but not least, total distance, total distance, total distance. I like this calculation. It's kind of fun. Total distance. This is not displacement. This is the total distance that we traveled. So what we need to figure out here is from first 3 seconds. So I need to figure out, where did my particle start? What position did it start at? Then did it ever stop? Then did it ever move? And then did it ever stop again? Okay, so what I mean by that is I need to figure out, where did we begin? So what's my position at time 0? Did our particle ever stop and change directions? Yes. our particle stopped at 2. So I need to figure out what's its position at time 2 seconds. Does it ever stop again? No, so that means it never changes direction again, so it just keeps traveling until 3 seconds. Now I think we already calculated all of these, so let's just go up above. X of 0 we got to be 3. X of 2, no, we didn't do that one yet, so we're going to have to calculate that. I don't think we did we? We did V of 2, we didn't do X of 2. So X of 2 would be 4, take away 8 would be -4, plus 3 is -1. And then X of 3, we already did that. I think it ended up being 0. Now, these numbers represents the position that our particle is at. Our particle at time 0 is 3 feet to the right. At time 2, our particle is 1 foot to the left of 0. Let me try again. This is 3 feet to the right of 0. This is 1 foot to the left of 0, and this one is actually at 0 feet on our horizontal line. So if I want to figure out the total distance traveled, I've got to figure out what happens in between each one of these. So from 0 seconds to 2 seconds, how far did we travel? We traveled 4 feet. Between 2 seconds and 3 seconds, how far did we travel? We traveled 1 foot. So then I would add those together and I would get a total distance of 5 feet. Now, how far did our particle actually move? Go back up to the very first one. Our particle, from beginning to end of 3 seconds, it moved 3 feet backwards to the left. I shouldn't say backwards, I should say to the left. In total, it moved from beginning to end, it moved 3 feet left. But it really went 5 feet because it went 4 feet forward. Sorry, it started at 3 feet forward, it went 4 feet backwards, and then went forward 1 foot. So it actually traveled a total distance of 5 feet. So our write-up would be the particle traveled, is it 2 L's or 1 L? I never know. Actually, I'm going to look, never mind. We can look it up later. The particle traveled a total distance of 5 feet. Now, you can't just say 5 feet. You have to say when. During the first 3 seconds. Now, there is some leeway here. You could say something like the particle traveled a total distance of 5 feet from time 0 seconds to time 3 seconds. I mean, if you wanted to say that, you could write it up. There is some leeway as long as you have the general gist of the statement. But this is the way that you're going to see that we're going to write these up, and it's just going to be the same write-up over and over and over again, the format of it. So I'm going to stop there, and we'll come back, and we'll try to hopefully get maybe more than one page done at a time.